I need to turn off the light. That's why.
There you go. Cool.
Yeah.
There we go. All right, so 15. So for 15, our second equation is already in y equals form. Our first one is not. So we need to get it in y equals form. So what's the first thing we should do here? Jaden, what's the first thing you did here to get it in y equals?
Move x to the other side.
Cool. So then what's our last step here? What's your name? I'm sorry. Julia. Julia, what do you think our last step here is? Good. So then what will that do with our sign? Good. So then -1 divided by -4 will give us a +1/4. And -10 divided by -4 will give us a +10/4. So now they're both in y equals form. So now we can go ahead and graph. So let's go ahead and graph the one we just made. So our y-intercept is 10 divided by 4. That's about 2.5. Plug it in your calculator. So there's our y-intercept, and our slope is 1/4. So I can go up 1 to the middle in here. 1, 2, 3, 4. And then we can draw a line through. And why is my line a straight line here? Or a little curvy, but why is it a solid line? Ava?
Because it's greater than.
Yes, is equal to makes this line solid. Good. All right, so now let's graph our absolute value. So what would our vertex be for y less than or equal to 3, x minus 1? What's our vertex going to be? Jaden?
1, 0.
Good. Because this negative is part of that formula. So our vertex is at 1, 0. And what is this 3 going to do? What is that going to do to our graph? The other, Ava?
It's so slow.
Yeah. So on our right side, our slope's going to be 3. And what about on the other side? Negative 3. Yep. 1, 2, 3. 1, 2, 3. Okay, so it'll be negative. So this is a vertical stretch. And will this line be solid or dashed? Gabrielle, do you think it'll be solid or dashed?
Which one?
Front one, Sol, right? Snyder. Solid, good. That's not a very good of a line. It's a little better. Awesome. All right, so now we need to shape. Let's go back to our line. Our y is greater than or equal to. So we are going to go to a point. We're going to go up. So we are shading above this line. And then for our absolute value, it's less than or equal to. So we are going to go to a point, we are going to go below, because it's less than or equal to. And this is all the points. So down here, over here, everywhere. Less than or equal to. Inside here would be greater than. So every point we're going less than. So then, we're the region where it's shaded in both areas, it's two different areas. So it's in here and on this side. So those are the two different regions where it's where both colors are shaded. This one's a little tricky. Any other questions on that? Go on. All right. So we're also going to do 45 or 47 was it?
47.
47. Fine. So they want us to graph the solution. We have two different x's in here and two different constants. Let's combine them. So what should we do first? Let's combine our x's. What are we going to do? Ella. Good. So it'll give us 12x. And then if we move this 2 over to the left-hand side, that will give us negative 15. Two things at once I'm doing. And so now to get this x alone, we're going to divide both sides by 12. So it's x less than or equal to. This is still negative, so we have negative 15 over 12. But what does that simplify to? Jaden?
5 over 4.
Good. Negative 5/4. And so then you'll just graph this on a number line. We know that this is a little bit over 1, negative. So we could go from negative 2. Just go up a few values. So then our negative 5/4 is about what value? Numerical, 1 and what? The other, Gabby?
Negative 1.25.
Yeah, which is about like right here. So we have a less than or equal to, or greater than or equal to sign. So are we gonna have an open circle or a closed circle? Could be equal to that value. So it will be a closed circle. And x is greater than or equal to this value. So your arrow would go greater than. And that's it for that one. Questions on this one? Yeah.
Could you graph it like on the that kind of graph?
So when you just have an x like this, just one variable, you can just use it on a number line.
Okay. Mm-hmm.
So we're just dealing with one variable, so just a number line. Any other questions?
Unless it specifically said the graph on a coordinate grid, it just gets graphed on it. So that was like an old review problem from chapter 1.
Good? Cool. Mhm.
So if you made corrections, please make sure you submit that assignment. Today, we are going to continue graphing, as I said, graphing systems of inequalities. So if you want to turn to the chapter 3 notes, We will see if we can graph some systems of inequalities that contain 3 or 4 inequalities, because a system is at least 2, but it could be 3 or 4 or 5 or 6. I think on Tuesday, I believe the one problem that you'll be graphing, it may have 6 or 7 inequalities that you'll be graphing. So the second part of chapter 3, there's like a little extension to section 3. So section 3.3 is graphing systems of inequalities, but then sometimes there's like an extension onto the section. Like in chapter 2, the piecewise functions was an extension of section 2.7. So linear programming is an extension on section 3.3, and sometimes we extend to just go like more in depth, more in detail with the concepts that we're talking about, and not just simply graphing. How can we apply the information? So today is more like practicing the graphing more inequalities. Monday would be more of the application part, where we really start pulling in like the application, the word problems, the real life situations as to why you would use an inequality or a system of inequalities. So today we're going to use systems of inequalities to find maximum and minimum values of a graph. So we will be looking at something called a constraint and something called a feasible region. And again, our goal would be to find a maximum or minimum value in this graph, because anything in the shaded region is the answer. But what if I need to find a minimum value or a maximum value to kind of like maximize a profit or maybe minimize a cost? How does a graph help us do that? And that's what we're going to look at. So the first word we see is constraints. Does anybody know, just like, think about not even like math, but if something has a constraint to it, what does that mean? Cody. That is exactly the word I was going to think of as well. Nice job, Cody. So a constraint is a restriction. You're being restricted to do something. That's a constraint. Maybe you broke your right hand. You're being restricted from writing using your right hand. You have that constraint. You cannot use it right now. So it's a restriction. In this case, it's a restriction on an equation. Or how about on the inequality? And it could be as simple as saying x has to be greater than or equal to 2. That's a restriction or a constraint. You're saying x must be bigger than this number. It's no longer allowed to be less than 2. So you're restricting the value for all of your x's. So it really is like a restriction, but kind of thinking of it as an inequality. The next thing we have here is this fancy term called a feasible region. If we're graphing a system of inequalities, what do you think the feasible region would be? So think about what your graphs looked like yesterday. Yeah, so Brooke said it's where they all overlap. That's that darkened region. So where all of our inequalities, all the shading is overlapping, it actually gets a name. It's called a feasible region. That's going to be where our solution exists. So today we're going to see if we can look at some constraints, which are really just a fancy way of saying an inequality. And we're going to see if we can get this feasible region. So it's going to be like a bounded region where the graph has these overlapping pieces. Before we do that, we're actually going to start with a bounded region. And right now this is blank, so I'm going to give you some points to plot. And we're going to try and use that bounded region or feasible region to help us determine maximum and minimum values. So we are going to just graph a couple of points here. I'm going to go over to 2 and let's go up to 5. So I graphed a point at 2, 5. And then why don't we stay on 2, and maybe we'll just go down and graph another point at 2, 1. So this point is at 2, 1. And we'll connect them. I'm just picking points. Points have no meaning. I just throw in a couple points up here. 1, 2, 3, 4, 5. Let's go up to 5 and over to 3. Or I'm sorry, over 5 and up 3. Come on, Mrs. Kane. And then we'll just graph one more. We'll do another one at 5, 1. So the feasible region, if I just graph these 4 lines, and they were all inequalities, and then there was shading involved, my feasible region is going to be that region where all of my inequalities meet, all of my shading meets, that overlapping area. So again, if we were to graph 4 lines and shade, this is what my answer would look like for a feasible region. It's just already given to us. Well, I made you draw it. So sometimes when you have a system, you will be asked to find maximum and minimum values of the system using an actual equation representing x and y. So this is an equation that represents x and y, and it's equal to c. Sometimes we place this equal to c to represent the cost. So if I was actually doing a word problem, that c probably means the cost of whatever I have to buy for my company. But I'm not applying that right now. We're just kind of getting used to what this looks like. So this equation here, not an inequality, I wouldn't graph it, but I'm going to use this equation to help find the maximum and minimum values. And the equation is called the objective function. That's our goal. So an objective is a goal to meet. So this is called the objective function. And we want to meet this goal by finding the maximum or the minimum of this objective function. So again, we're not graphing this, but we're going to see if we can find what the maximum and the minimum values would be. Now, here's my little grid area, my feasible region. Where do you think a maximum value or a minimum value would lie? So if I wanted to get x values and I wanted to plug them into this equation, where do you think a maximum value would be with a pair of x values, or a minimum value would be with a pair of x values? Brooke? Further, so she said furthest away from the origin. That's a good, yeah, good, probably. They're thinking like further away from the origin, because you have more positive numbers. What else do you think it could be? Jane?
Kind of what she said, but of the shaded region, the highest to be farthest to the right and the lowest to be farthest to the left.
Okay, yeah, so looking at the shaded region, do you think it would be one in the middle here? If it's in the middle, it's probably going to give me an answer that's in the middle of my max and the min, because it's in the middle of the shaded area. So our max and mins actually come from these points. Does anybody know from geometry when 2 lines connect? What are those points called? It's also in the absolute value graph when it meets at the bottom. Vertex. Each one of these are called vertices. So those points where 2 lines meet are called vertices. The vertices help us determine the maximum and minimum values. They're either going to represent a max or a min. Anything in the middle would be a value in the middle. So if it's in the middle in my shaded area, then it's going to give me an average number. But if it's one of these vertices, it's on the outside. It's bounding my area. It's stopping that graph from going any further. Then it's going to give me a max and min. So the way we find this is by making a little T-chart, listing our vertices or our ordered pairs, and plugging them in to see what the actual cost is. The lowest values, I said C for cost, because when I see C, I just think cost. And that's just like a math thing, I guess, that I think about when I write functions. So see if you can take the ordered pairs that are up here, those vertices, find out which ordered pair gives us the maximum and which one gives us the minimum value. So again, you have those ordered pairs, those are called vertices. Two lines connect, makes a vertex, pluralized vertices. Plug them into our equation. This is our objective function, it's our goal. We want to see if we can have the minimum or the maximum of this goal. So we're taking those ordered pairs, plugging them into our objective function. The answer, whichever one is biggest, obviously is the max. So that ordered pair would produce the maximum cost of C represented cost. Or the ordered pair would represent the minimum cost. Gabby Soul, do you have answers?
Yeah.
What do you have?
The first one is 9.
This one?
Yeah.
Are you sure?
No. 7. Like, oh my god.
How about we'll meet in the middle?
Hey,
Okay.
my tongue thing is not working.
That's all right. It's okay. It's still really early. How about the next one? You have that one?
16.
So 15 and 2.
3 times 5. I did my order differently.
Oh, no. Okay, so you have the opposite. Okay, so let's see. Do you have this one as 16 then?
Yeah.
And then what's the one here in the middle?
3 times 5 is 15, and then plus 6 is 21.
There you go. So kind of looking to see what everybody thought, you were thinking if it's furthest away from the origin, then it probably is going to give us the max. And at this point here, I mean, that's furthest away and it's also kind of up vertically. So that would be our maximum. So right here, that ordered pair at 5, 3 gives us our max. 2, 1 was the one that was closest. And you can see from the ordered pair of 2, 1, that is our minimum value. Again, if we found a point in the middle, it would be in the middle of all of them. It's not going to be my max, it's not going to be my min. And some of the other values are also in the middle. So the 15 or the 17 and the 16 points, they're also in the middle of my max and min. But the max and min will be from one of those vertices. A max would be one of them, a min would be one of them. It's never going to be in the shaded region. So that's called finding max and mins given an objective function. So we are going to continue now. We're going to see if we can actually graph something like this. So the graph here, we didn't actually graph any inequalities. So let's see if we can now graph some. Question?
So
Yeah.
just to ask, is that all we have to do to write our answers?
Yeah.
Just like,
Yep, that's it. So find the minimum. We found the minimum value at 2, 1. It's equal to 8. We found the maximum value of 5, 3. It's equal to 21. That's it. Other questions? All right, so let's see if we can now graph some. There's 2 examples here. Example 1, I have X and Y. Example 2, I use C and D just to get you to realize that it doesn't always have to be X and Y. I mean, there are other letters in the alphabet. We might as well give them some love too. X and Y gets all the attention. Why not some other variables? So you see now that this is a 4 inequality system. The first 2 say X and Y are greater than or equal to 0. And then we have X plus Y is less than or equal to 6. 12X plus 6Y is less than or equal to 48. It wants us to grasp the feasible region. So that's that bounded area where everything intersects, overlaps. And then it also says label each vertex. So now we're going to be focusing on where are they meeting and we're going to label them. So the first thing we need to do is somewhere place an X and Y axis in here. And I'm not going to go in the center. The reason I'm not going to go in the center is because it's telling me X is greater than or equal to 0 and Y is greater than or equal to 0. This means my X has to be positive, my Y has to be positive.
So I'm not looking at the negative regions of the graph. So when I make my X and Y axis, a little more, I'm just gonna come over here a little bit. So I just went over 3 and I'll go up 3. And again, the reason I'm doing that is I'm just looking at those first 2 inequalities. And I'm noticing it's saying that they have to be bigger than 0. Anything bigger than 0 must be positive. So here's my x-axis, and here's my y-axis. So from the first 2 inequalities, x is greater than or equal to 0 would mean that my graph has to be in this portion here. My x's must be bigger than 0. So everything on the right side is bigger than 0 for x. My y's are greater than 0, means that it has to be above here. So I'm not going to shade this whole region, because then my whole graph will be shaded. And I'm just reminding myself with those little arrows. See if you can graph the other 2 inequalities. Get y by itself, graph those other 2 inequalities. So the first 2, vertical, horizontal line. The x is vertical box. The y is horizontal. So we have constraints or restrictions on x and y, forcing them to be positive. Julia, what did you get for that last inequality when you solved for y? Did you have that solved? The 12x plus 6y is less than or equal to 48.
I got y is less than or equal to negative 2x plus.
What's 48 divided by 6? Yeah. Do you remember when you did those are they like minute tests where you took? Yeah. Ella's like, please don't do that.
Those things gave me so much stress in like 3rd grade.
Yes, that's when I think they started in about 3rd grade, maybe the end of 2nd. My 4th grader now, they're, of course, now that everybody has an iPad, there's this app called Reflex Math, and it's like it's a gaming system. So she loves it because it's games, but it's still like on multiplication skills, and you have to be fast. And if you're not fast enough, then it like bumps you off from knowing that fact. But it keeps track of all the facts in a pyramid, and you still have to like practice and know them. So instead of taking those tests in class, they now get like tested on the app as to how far they get each week, how many facts they cover. So it's a little better, Ella, than like forcing you to like click in a minute to do those facts.
I remember the teacher said like 30 seconds left and I'd only be like halfway done.
Like, oh my gosh, what am I gonna do? Yeah, that's a little pressure on those kids, especially at that age. My oldest daughter, she had those tests, but the younger one got lucky because the app was found and implemented. All right, so let's graph this first one. We're going up to 6 and placing a point. That's my intercept. The slope with that is a -1, so down 1, right 1. And I'm going to go all the way down until I connect with the x-axis. So Ava, R less than or equal to means solid or dashed line? Solid, yeah. And I'm actually not going to draw any more of the line. You can, it's not wrong. But I know that nothing can be beyond this vertical line, x is 0, or below the horizontal line. So I'm just gonna stop there. Again, feel free, it's okay, you're not wrong if you go beyond it. But I know my graph can't go beyond that, my answers can't go beyond that, because x and y must be bigger than 0. The next one I have to graph up here at 8, and now I'm going down 2 and right 1. I notice they connect, so I'm really kind of bolding that area where they connect. Both of these say less than or equal to. If you have like a highlighter on that iPad of yours, like you can kind of highlight the area, you could draw little arrows, whatever helps you. But both of these must be less than or equal to. So I must be less than all of my lines, my diagonal lines, I should say. And remember, we're now looking for a region. So if I'm underneath my blue line and underneath my purple line, the region and just be careful up above. It's now this quadrilateral region. So again, below the blue, but then it has to still be below the purple. And it's hard to think below when you have such a steep line, but just think you're going underneath the points of that line. Below is underneath every point on the line. So this should be my graph right here. Hopefully yours looks a little better than mine. The last part of it said label each vertex, or label the vertices if I wanted to pluralize it. So underneath, I would just place those vertices. How many are there? How many times do they meet? Lacey, how many vertices do you see?
3.
So we got 3. Can you give me them, Lacey?
1 is 0.
Yeah, 1 is 0, 0, because it meets right there at the origin. That's where x and y are greater than 0. Okay, there's another one. 4, 0. And that's this point right here where my line is connecting. The first line is connecting with the x-axis. How about another one?
6, 0.
6, 0. And then is there one more? How about this guy right here? My 2 lines crossed at that value as well.
Is it 2? 4.
Yeah, 2, 4. Nice job. Question.
What about the points on the y-axis?
So the points, I think she just flipped this. We'll flip it around for her. How about 0, 6? 1, 2, 3, 4, 5, 6, yeah. So that point should be 0, 6. Thanks. So that point on the y-axis is at 0, 6. So we're not using the point way up here because that's not part of my bounded region. We're not using this point over here because that's not part of my bounded region. So we want this feasible region that's connecting directly with that quadrilateral. Any questions? So we're going to try and graph one more, but it's graphing C and D instead of X and Y. Ordered pairs are written alphabetically. So X is independent, it's first, Y is dependent, it's second. So when I look at this first problem here, it says 1 is less than or equal to C, which is less than or equal to 4. C is first in the alphabet. It's independent. It's really my X variable. Does anybody know what that inequality is telling you? 1 is less than or equal to C, which is less than or equal to 4. What is that saying? Or if I had 1 is less than or equal to X, which is less than or equal to 4. Jaden, what's that saying?
That the x values can only be between 1 and 4.
Yeah, perfect. So the X values have to be between 1 and 4. So again, I'm going to go and make my line. I'm going to just do the same thing I did before. All right, and I'm going to call this my C and my D instead of X and Y. So she said your X values have to be between 1 and 4. Okay, so think x. I need to go over to where x is 1. Right here it's 1. And then over to 4. Right here it's 4. My graph has to be between those two values. When I have values for x, it's vertical lines. So I'm going to make 2 vertical lines at 1 and at 4. My answer is going to be in between those 2 vertical lines. Because if I look at my inequality, the way it's written, it's in between those 2 numbers. So my graph should be shaded in between there. Because my variable is in between the values.
Sorry, this is just like a scenario, but say there was only a less than sign in that problem, would it be a dotted line? then?
Yes,
Is that
it
okay?
would, yes.
I just wanna-
That is exactly right. So if there was just a less than sign, we would make a dotted line, exactly. All right, let's keep on solving. So x is c, the first variable is your independent. That means the d represents y, that's what we're solving for, that's the dependent. So d is less than or equal to negative c plus 14. So we're gonna go all the way up to 14, and we should have enough space here. So I went all the way up to 14. And then the slope, it says, is negative 1. So down 1, right 1. And you don't have to draw the whole line. Maybe the less might make it less messy. But I'm going to make my line at least go through the 2 vertical lines, because I know my answer is going to be in between those 2 vertical lines. So my answer has to be between my 2 vertical lines. The last part here says D is greater than or equal to 2C. What's the y-intercept value of that last inequality? Anybody know? Like, what is the y-intercept back here?
Zero?
Yeah, it's 0. There isn't one. The one above has a 14. This one doesn't have one, so it starts at 0. So going down at 0, the slope is up 2 over 1. It's 2 times c. So y-intercept 0, it doesn't have one. And then up 2 over 1. So my answer has to be in between the 2 lines. In between my 2 vertical lines. It has to be less than my line that went above and greater than that last line that I just drew. So carefully try and shade it in. It does get more difficult trying to shade in your values when you have more inequalities to look at. And then the last thing I'd like you to try and do is to write those points where the 2 lines are connecting. And they connect at 4 nice points. So see if you can write those 4 points. So the homework for the weekend will be to graph 4 of these problems. So you're going to graph 4 of them. I have graph paper on here, but if you use Notability and just pull that graph paper into Notability, like, it's a great tool to use to help you graph, because you can make your own XY axis. There are also 4 questions on that worksheet that kind of get you to build your own equations. So they're like think about it questions. You're not going to be graphing them, but you're going to kind of be making your own equations based off of this, or inequalities based off of the scenarios that would be given. So again, 4 graphs for your homework tonight. And then there's 4 other questions that it's going to kind of ask you. So looking at my ordered pairs, I have a point at 1, 2. That's this first point here. I have a point at 4, 8. And then at 4, 10. And then I think I have another point at 1:13. Again, those would be our vertices. Questions? So we will do a little more of this on Monday, but we're gonna have a word problem. So Monday, we're gonna have 2 word problems. We're gonna write our own inequalities from the word problem. We're gonna graph the inequalities. And then we're gonna do what we did for that first problem. So we're gonna kind of build on the 2 things we did today. So the first problem here, we did this max and min. We're gonna do that on Monday. It's gonna be one big problem. So we'll graph, we'll do the max and min part. Let's see if we can find an answer. Questions? Does anyone at home have questions? So hopefully you all have a fantastic weekend. It's gonna get colder. I think the high for today is 50 something. Tomorrow is 50 something. Sunny tomorrow, but colder. Okay. You never know with Mr. Cummings, he might scarf it up. Yeah. Mr. Cummings is known to be a messy guy. No? He's pretty neat and organized, huh? I know, Lacey, you had class in here last year.
No, I had like Mr. Thomas.
Yeah, did you have it in here?
No.
No, it was in a different room.
I had it.
You had it in there, okay. You know,
Right.
Landon was right behind you the whole time? Yes. Have a great day. Great weekend. See you guys next week. See ya. Thanks, you too.